Hello there, and welcome to the Sleep with Science channel, where tonight we are going to take you somewhere far beyond the reach of ordinary thought, far beyond the pale blue we call home, far beyond even the furthest star your naked eye has ever traced on a clear and quiet night. Tonight, we are going to travel to the very edge of what humanity knows, to the trembling boundary where science meets wonder, where mathematics dissolves into mystery, and where the universe, ancient and vast beyond all comprehension, has done something that no one was prepared for. Something that, by every law we thought we understood, simply should not be there. So let yourself settle now. Let your body sink a little deeper into wherever you are resting. Feel the weight of the day beginning to lift, slowly, gently, the way morning fog rises off a still lake without any hurry at all. Let your shoulders drop. Let your jaw soften. Let your breath find its own quiet rhythm, because we are not going anywhere fast tonight. The universe does not rush, and neither will we. Close your eyes, if you haven't already. Imagine darkness. Not the darkness of a room with the lights off, not the darkness behind your eyelids, but a darkness so complete, so ancient, so perfectly silent that the very concept of sound seems like something that was only ever invented here, on this one small world, and has no meaning whatsoever out there. This is the darkness of deep space. The darkness between galaxies. The darkness that existed before the first stars were born, when the universe itself was young and formless and still catching its breath after the incomprehensible violence of its own beginning. 13.8 billion years ago, everything that exists, every atom in your body, every photon of light that has ever warmed your skin, every grain of sand on every beach on this earth, exploded outward from a single point of infinite density. And in those first moments, the universe was unimaginably hot, unimaginably bright, and unimaginably small. But it expanded. It cooled. And slowly, over hundreds of millions of years, the darkness that followed began to fill with something extraordinary. Gravity pulled hydrogen together. Clouds collapsed. Pressure built and built and built, until, deep inside those collapsing clouds, something ignited. The first stars were born. And for the very first time in the history of everything, the universe had light. We call that era the cosmic dawn. And for a very long time, we could only imagine it. We could theorize, we could calculate, we could build models and run simulations and argue over equations, but we could not see it. The light from those first galaxies, those very first structures that gravity ever assembled, had been traveling toward us for so long, across such incomprehensible distances, that by the time it reached us, it had stretched. It had shifted. The expansion of space itself had pulled those ancient photons into wavelengths far longer than visible light, into the infrared, into frequencies invisible to human eyes and to every telescope we had ever built before. And so the cosmic dawn remained hidden, a chapter of the universe's story that we knew existed but could not read. Until now. Somewhere above this quiet earth, drifting in the cold and the silence approximately 1 million miles from where you are lying right now, there is a machine unlike anything our civilization has ever constructed. It is the size of a tennis court. It is wrapped in a golden mirror 21 feet across, made of 18 perfectly shaped hexagonal segments coated in a layer of gold so thin it would take 1,000 of them stacked together to equal the width of a single human hair. It is shielded from the warmth of the sun by a sun shield the size of a tennis court, layered in 5 sheets of a material so thin and so delicate it trembles at the threshold of imagination. It operates at a temperature colder than anywhere in our solar system, colder than the surface of Pluto, colder than the dark side of Mercury, because it has to. Because the light it is listening for is so faint, so ancient, so impossibly far away, that even the warmth of its own instruments would drown it out. This is the James Webb Space Telescope, and it has been seeing things. Things that were not supposed to be there. Things that arrived in the early data and made astronomers stop, go quiet, and read the numbers again. things that peer review committees looked at with furrowed brows and careful words, and a certain unmistakable undercurrent of something that, in the usually cautious and measured world of professional science, can only be described as disbelief. Because the universe, it turns out, was doing something in the very beginning that our best models, our most carefully constructed theories, our most elegantly tested frameworks of cosmic evolution did not predict. Could not predict. Galaxies that are too large, too bright, too structured, And the question that has begun to move through the astronomy community, spoken sometimes in papers and sometimes in conference hallways and sometimes in the quiet aftermath of a long night spent staring at data that refuses to behave, is not a small one. The question is whether what Webb has found means that something in our understanding of how the universe builds itself, how gravity works, how stars form, how time itself has unfolded since the very beginning, needs to be reconsidered. Quietly, carefully, but reconsidered nonetheless. And tonight, in the stillness that surrounds you now, we are going to explore exactly that. We are going to walk, slowly and gently, through what the James Webb Space Telescope has revealed, what those revelations mean, and why the scientists who have spent their entire careers building the most precise and beautiful picture of cosmic history ever assembled are now holding that picture up to the light and noticing, for the first time, that some of the pieces do not fit. But there is no hurry. The universe has been keeping this secret for 13 billion years. It can wait a little longer while you breathe, and soften, and let the day fall away from you like a coat you have finally been given permission to set down. So let us begin at the beginning. Not the beginning of the telescope, not the beginning of the discovery, but the beginning of everything. Because to understand why what Webb found is so extraordinary, so quietly world-altering in the way that only the deepest scientific revelations can be, you first need to feel the scale of what we're talking about. And scale, in cosmology, is not something the human mind grasps easily. It is something you have to be eased into, coaxed into, the way you ease into sleep itself, not by forcing it, but by letting the layers of ordinary awareness dissolve one by one until something deeper and quieter takes over. The observable universe, the portion of everything that exists that light has had enough time to travel across and reach us since the Big Bang, is approximately 93 billion light-years in diameter. A light-year is the distance light travels in a single year, moving at 186,000 miles per second. In 1 second, light could circle the entire Earth 7.5 times. In 8 minutes, it crosses the distance between the Earth and the Sun. In 4 years, it reaches the nearest star beyond our own. And the observable universe stretches 93 billion of those years in every direction. There are, within that observable universe, an estimated 2 trillion galaxies. 2 trillion. Each one a vast, slowly spinning city of stars, dust, gas, and mystery. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. And the Milky Way is not a particularly large galaxy. It is average, medium-sized, one of 2 trillion. Breathe that in for a moment. Let the numbers wash over you without trying to hold them. You are not meant to contain them. You are only meant to feel them, the way you feel the depth of the ocean, not by measuring it, but by standing at its edge and understanding, in your body, that it goes down farther than you will ever see. Within all of that vastness, within those 2 trillion galaxies spread across 93 billion light-years of space and time, the James Webb Space Telescope was pointed at a patch of sky. A specific, carefully chosen region. And it gathered light. Ancient light. Light that had been traveling toward us since before the Earth existed, before the Sun was born, before the Milky Way had taken its current shape. Light that left its source when the universe itself was only a few 100 million years old. An infant. A newborn, cosmically speaking, still figuring out its own laws, still building its first structures from the raw materials the Big Bang had scattered in every direction. And in that ancient light, Webb found galaxies. That, on its own, is not surprising. We expected to find galaxies. That was the entire point. That was what Webb was built for, in part. To peer back to the cosmic dawn and capture the first faint light of the universe's earliest structures, to see what the very first galaxies looked like, how small they were, how chaotic, how simple, how young. The surprise was not that the galaxies were there. The surprise was what they looked like. Because the galaxies that Webb found in that ancient light, those extraordinarily distant objects whose light had been traveling for over 13 billion years before landing on Webb's golden mirror, were not small. They were not faint. They were not chaotic or primitive or simple in the way that our models told us the very first galaxies should be. They were large. Some of them were shockingly, almost impossibly large. Massive structures containing hundreds of billions of stars, already formed, already ordered, already glowing with a brightness and a complexity that, according to everything we understood about how gravity works and how long it takes stars to form and how slowly the universe was supposed to build its earliest architecture, should not have been possible. Not yet. Not that early. Not in a universe that was only a few 100 million years old. It would be a little like digging through the foundations of an ancient city, expecting to find primitive tools and simple pottery, the first rough attempts of early civilization, and instead uncovering a skyscraper. Fully built. Fully wired. With elevators running and lights on in every window. In a layer of Earth that, by every geological method we have ever trusted, dates back to a time before human beings existed. Before language. Before fire. Before the first tentative steps of anything we would recognize as thought. That is the scale of the contradiction. That is the size of the question that Webb has placed, quietly and without any fanfare, into the hands of the people who have spent their lives trying to understand how the universe builds itself. And it is not a small question. It is not a question with an easy answer waiting just around the corner. It is the kind of question that, when it arrives in science, tends to arrive slowly, dressed in data rather than drama, and tends to change things in ways that take years, sometimes decades, to fully understand. But we are getting a little ahead of ourselves. And tonight is not a night for rushing. Tonight is a night for floating. For drifting. For letting the mind move through ideas the way a leaf moves through still water, without effort, without destination, carried gently by something larger and quieter than itself. So let us slow down again. Let us return to the telescope itself, because there is something deeply beautiful about what this instrument is and how it came to be, and that beauty is worth sitting with for a while before we go any further into what it found. The James Webb Space Telescope was not built quickly. It was not born from a sudden inspiration or assembled in a hurry. It was conceived in the late 1990s, when the previous great eye on the universe, the Hubble Space Telescope, was still relatively young, and when astronomers were already dreaming of something more powerful. Something that could see further back. Something that could reach into the infrared and pull back the curtain on the cosmic dawn. It took over 20 years to build. 20 years of engineering challenges so complex that the project nearly collapsed under its own ambition more than once. The sun shield alone required the development of entirely new materials. The mirror, that great golden honeycomb of 18 beryllium segments, each one polished to a smoothness measured in nanometers, had to be designed to unfold in space, precisely and perfectly, like an enormous mechanical flower opening in the dark, because it was far too large to fit inside any rocket in its fully assembled form. And then, on Christmas Day of 2021, it launched. Sitting atop an Ariane 5 rocket at a launch site on the northeastern coast of South America, it rose into the sky and disappeared into space, carrying with it the hopes and the fears and the decades of work of thousands of scientists and engineers and dreamers from across the world. And for the next several weeks, the entire astronomy community held its breath, because everything had to work. Every single one of the 344 individual mechanisms that had to deploy correctly in sequence, any one of which, if it failed, could have ended the mission entirely. 344 points of potential failure, and the telescope had to survive every single one of them. It did. The sun shield unfolded. The mirror segments clicked into position. The telescope cooled, slowly and patiently, down to its operating temperature of -448 degrees Fahrenheit, just a few degrees above the coldest temperature that physics allows to exist anywhere in the universe. And then it opened its eye. The first full-color images were released to the public in July of 2022. And the world, for a moment, went very quiet. Not the quiet of disappointment. The quiet of awe. The quiet that descends when something exceeds not just your expectations, but your capacity for expectation. When what you are seeing is so far beyond what you had prepared yourself to see that your mind simply pauses, the way it sometimes pauses at the edge of a dream, suspended between one state and another, not quite sure which direction is forward. One of those first images showed a galaxy cluster called SMACS 0723. A dense collection of massive galaxies relatively close to us, cosmically speaking, whose combined gravity bends and magnifies the light passing through them from galaxies far behind, acting as a natural lens, a phenomenon Einstein predicted over a century ago called gravitational lensing. And behind that cluster, stretched into glowing arcs of light by the curvature of space itself, were galaxies. Hundreds of them. Some of them among the most distant objects ever observed by human instruments. And every single point of light in that image, every smear and arc and tiny smudge of color, was not a star. It was an entire galaxy. Billions of stars compressed by distance into a single pixel of ancient, traveling light. People cried when they saw it. Scientists who had worked on the telescope for decades cried. Not because it was sad. Because it was beautiful in a way that the word beautiful does not quite reach. Because it made the universe feel simultaneously enormous beyond all comprehension and somehow, impossibly, intimately close. Like pressing your eye to a keyhole and finding, on the other side, not a room but everything. And that was only the beginning. Because as the data continued to come in, as the early release observations gave way to the first scientific papers, as astronomers around the world began downloading and analyzing what Webb was sending back, something else began to emerge from the data. Something quieter than the beautiful images. Something that lived not in the pictures themselves, but in the numbers behind them. In the spectroscopic readings, in the redshift measurements, in the careful and painstaking analysis of light that had been stretched and shifted and transformed by billions of years of cosmic travel before it finally arrived at Webb's waiting mirror. And what was emerging, slowly and with the particular kind of reluctance that real scientific discovery always carries, because real discovery never announces itself loudly, it always whispers first, what was emerging was a pattern. A pattern that did not fit. A pattern that the models had not predicted and the simulations had not produced and the theorists had not prepared for. A pattern that was making some of the most careful and rigorous minds in modern astronomy do something that careful and rigorous minds are specifically trained not to do. It was making them wonder if they had gotten something fundamentally wrong. But before we follow that thread, let us rest here for a moment. Let us stay with the telescope itself, with the quiet miracle of its existence, because there is a quality to the story of Webb that mirrors something about the nature of sleep itself. Both require patience. Both require surrender. Both ask you to let go of the ordinary world and trust that something extraordinary is waiting on the other side of the threshold. The Webb telescope did not arrive at its final destination quickly. After launch, It traveled for 30 days through space, covering the 1 million miles between Earth and its resting place, a gravitationally stable region of space called the second Lagrange point, or L2, where the combined gravity of the Earth and the Sun holds it in a kind of permanent, gentle equilibrium. A cosmic hammock. A place where it could float, stable and cold and perfectly positioned, with the Sun and Earth and Moon always behind it, always on the same side, so that its sun shield could protect it from their warmth indefinitely. 30 days of travel. And during those 30 days, the telescope was deploying itself, unfolding piece by piece in a sequence so carefully choreographed it reads almost like a piece of music. The pallet hinges released. The sun shield layers separated and tensioned. The secondary mirror unfolded on its 3 long booms and locked into place. The port and starboard primary mirror wings rotated outward and clicked home, each step dependent on the one before it, each success making the next one possible. Like a story that can only be told in order, each sentence requiring the one that came before it to make any sense at all. And now it floats there. Right now, as you lie in the warmth and quiet of wherever you are, as your breathing slows and the world outside your window settles into its own nocturnal rhythm, the James Webb Space Telescope is out there in the dark, 1 million miles away, pointed at some ancient corner of the universe, collecting photons that have been traveling since before the Earth existed. It does not sleep. It does not rest. It simply watches, patiently and perpetually, with a stillness that feels almost deliberate, almost meditative. There is something comforting about that, if you let yourself feel it. Something deeply settling about the knowledge that while you rest, while you drift toward sleep, this golden instrument is out there doing what it was made to do. Looking backward through time, gathering light, building, photon by photon, a picture of the universe that no human eye has ever seen before. And the picture it is building is a strange one. Stranger, in certain ways, than anyone expected. To understand why, you need to understand something about how astronomers thought the early universe worked. About the model that, before Webb, represented the best and most thoroughly tested framework for cosmic evolution that science had ever produced. It is called the lambda cold dark matter model, though most people who work with it every day simply call it the standard model of cosmology. And it is, by almost any measure, a spectacular achievement of human understanding. It begins with the Big Bang and traces the development of the universe forward in time with extraordinary precision. It accounts for the large-scale structure of the cosmos, the way galaxies cluster together in vast filaments and sheets and walls separated by enormous empty voids, a structure so consistent and so mathematically describable that we have given it a name. We call it the cosmic web, and the standard model predicts it beautifully. It predicts the ratios of hydrogen and helium in the early universe. It predicts the temperature and the pattern of the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space and that we can still detect today as a whisper of microwave radiation coming equally from every direction in the sky. It predicts the accelerating expansion of the universe, driven by the mysterious pressure we call dark energy. It predicts the way dark matter, that invisible and still deeply mysterious substance that outweighs all visible matter in the universe by a factor of roughly 5 to 1, it predicts the way dark matter forms the gravitational scaffolding around which galaxies assemble themselves. The standard model predicts all of these things. And in test after test, observation after observation, decade after decade of increasingly precise measurement, it has held. It has been one of the great triumphs of human thought. A framework so elegant, so quietly powerful, that many scientists spent entire careers working within its boundaries without ever seriously questioning its foundations. Not because they lacked imagination, but because the model kept working. It kept matching what we saw. It kept predicting what we hadn't yet seen. And so the confidence grew, slowly and naturally, The way confidence always grows when something keeps being right. But science has a long memory. And it also has a long history of moments when the thing that kept being right suddenly wasn't. Not dramatically. Not all at once. The universe rarely announces its contradictions with fanfare. It tends instead to whisper them. A small discrepancy here. A number that doesn't quite fit. An observation that sits at the edge of the data, quiet and unexplained, waiting for someone to look at it long enough to understand that it isn't noise. That it isn't an error. That it is, in fact, a message. James Webb was built to receive messages like that. When it was finally positioned at its observing point, a place in space called the second Lagrange point, a gravitationally balanced location roughly 1,000,000 miles from Earth where the telescope could maintain a stable orbit while keeping the Sun and the Earth and the Moon always behind it, always on the same side, allowing its enormous sun shield to block their heat and their light and keep its instruments cooled to temperatures near absolute zero. When it settled into that position and opened its golden eye for the first time, there was a particular question that astronomers most wanted it to answer. They wanted to know what the first galaxies looked like. Under the Standard Model, the answer was fairly well understood, or at least, fairly well predicted. In the early universe, the thinking went, things were smooth and hot and nearly uniform. Matter was spread almost evenly through space, with only the faintest variations in density, ripples left over from the quantum fluctuations of the first instance of existence. These ripples were small, extraordinarily small. And as the universe expanded and cooled, gravity began its slow, patient work of amplifying them. Regions that were ever so slightly denser than their surroundings began to pull in more matter. Dark matter halos began to form. Gas began to fall into them and cool and condense and eventually ignite into the first stars. Those first stars were enormous and violent and short-lived, burning through their fuel in millions of years rather than billions, seeding the universe with the first heavy elements when they died. And then, gradually, across hundreds of millions of years, those early stellar populations began to cluster into the first primitive galaxies. Small, irregular, chaotic, slowly merging and growing over cosmic time into the grander structures we see around us today. That was the expectation. Small, faint, distant, primitive. The first galaxies were supposed to be the universe in its infancy. Rough and unformed. Still in the process of becoming. What James Webb found was something else entirely. In its earliest deep field images, released in the summer of 2022, the telescope showed us galaxies at distances we had never seen before. Galaxies whose light had been traveling toward us for more than 13 billion years. Galaxies that existed when the universe was only a few 100 million years old, a small fraction of its current age of roughly 13.8 billion years. And these galaxies were not what the models predicted. They were too big, too bright, too massive, too structured, too complete. Some of them contained hundreds of billions of stars. Some of them showed signs of having already undergone multiple generations of star formation, already containing older stellar populations, already enriched with heavy elements that take time to produce, already organized into recognizable shapes. Disk-like forms. Compact but coherent structures. Galaxies that looked, in some ways, not entirely unlike the Milky Way. Except that they existed at a point in cosmic history when, according to everything we understood about how galaxies form, they should not have had nearly enough time to become what they were. The universe, it seemed, had grown up far too fast. The astronomical community responded with the appropriate mixture of excitement and caution. These were early results. The data needed verification. The redshifts, those critical measurements of how far the light has been stretched by the expansion of space, a stretching that tells us how far away a galaxy is and therefore how far back in time we are seeing it. Those redshifts needed to be confirmed spectroscopically. It was possible, some argued, that some of these objects were closer than they appeared, that the photometric estimates, the estimates based on the colors of the light rather than the detailed analysis of its spectrum, might be overestimating how distant some of them truly were. It was a reasonable concern, and science required that it be taken seriously. But as the months passed and the follow-up observations accumulated, and as the spectroscopic confirmations began to come back, the picture did not soften. If anything, it sharpened. Galaxy after galaxy was confirmed at extreme distances. The redshifts held. The masses, estimated through multiple independent methods, remained uncomfortably high. And a few objects in particular began to attract very serious attention. Objects that sat so far from the predictions of the Standard Model that researchers began to use language they rarely use. Language that carries real weight in science. They said these galaxies were impossible. Not metaphorically, not casually. The word was used with intention, with the specific weight that scientists give it when they mean something precise. When they mean that an observation does not merely challenge a model, but stands in direct and unresolved conflict with it. When they mean that if the observation is real and confirmed, and not the result of some subtle instrumental error or some unconsidered bias in the data, then something in our foundational understanding of how the universe works must be wrong. That is a remarkable thing to say. It is the kind of thing that gets said rarely in science. And when it does get said, when it escapes the careful hedging and the qualified language that scientists rightly prefer, it tends to mean that something genuinely significant is happening. Something that deserves not just attention but stillness. The kind of stillness that comes before a very deep thought. So let us be still for a moment, and let us think about what impossible actually means in this context. The Standard Model of Cosmology, the Lambda CDM model, makes specific predictions about how quickly structure can form in the early universe. Those predictions are not arbitrary. They emerge from the physics of gravity and the physics of light and the physics of matter interacting across cosmic scales. They emerge from what we know about the density of dark matter and the temperature of the early universe and the rate at which it was expanding. All of these things constrain how fast galaxies can grow. They set a kind of speed limit on cosmic evolution. And that speed limit is not a loose estimate. It is a mathematically derived boundary, embedded in the equations, tested against observations made across decades with instruments that grew steadily more powerful and more precise. The galaxies James Webb found appear to have broken that speed limit. Not by a little, by a great deal. One way to understand the problem is to think about what it takes to build a galaxy. You need matter. Dark matter to provide the gravitational framework, ordinary matter to fall into it and cool and form stars. But you also need time. Time for the dark matter halos to grow massive enough through the slow accumulation of smaller structures. Time for gas to condense. Time for star formation to begin and proceed through multiple generations. Time for the light of those stars to fill the galaxy and make it luminous. The Standard Model gives you a budget of time for all of this, and in the early universe, that budget is extremely tight. A galaxy seen at a redshift of 10, for example, is being observed as it existed when the universe was roughly 450 million years old. That sounds like a long time, and measured against a human life, against the whole of recorded history, it is almost incomprehensibly long. But measured against the timescales of galaxy formation, it is extraordinarily brief. It is, cosmically speaking, a very early morning. The universe had barely begun to wake up. And yet in that early morning, Webb was finding galaxies that looked not like infants but like fully formed adults. galaxies that had already lived long and complicated lives. Some of the most striking examples were identified in a study published in early 2023 by a team led by astrophysicist Ivo Lab and his colleagues. They identified a collection of objects in the Webb data that, if their distances and masses were correctly estimated, would be extraordinarily difficult to explain. The most massive of them appeared to contain stellar masses comparable to the Milky Way, or even exceeding it, at a point in cosmic history when the universe was less than 1 billion years old. The researchers calculated what fraction of all the available matter in the observable universe at that time would need to have been converted into stars in order to build these galaxies. And the number they got was startling. In some cases, the fraction approached or exceeded 100%, which is to say, the galaxies appeared to require more mass in stars than the standard model allowed to be available for star formation at that epoch. The universe, in other words, seemed to have spent more than it had. That is the kind of result that stops people. That lands in a room of cosmologists and creates a particular quality of silence. Not the silence of dismissal. The silence of recognition. The slow, careful recognition that something here requires explanation. That the data is asking a question the existing framework cannot comfortably answer. Now it is important, here in this quiet and this darkness, to hold that recognition gently. Science is not a collection of certainties. It is a process. And part of that process involves sitting with anomalies, examining them from multiple angles, testing them against alternative explanations, asking whether the data itself might be leading us somewhere unexpected, not because reality has violated the rules, but because we have misread something, misunderstood something, left something out. There are several ways the apparent impossibility of these early massive galaxies could be resolved without requiring a fundamental revision of the standard model. Perhaps star formation in the early universe was simply more efficient than our models assume. Perhaps the initial mass function, the distribution of stellar sizes produced in each burst of star formation, was weighted differently in the early cosmos, producing more light per unit of mass. Perhaps feedback mechanisms, the processes by which young stars and black holes regulate and sometimes suppress further star formation, were weaker in those early environments, allowing gas to collapse and ignite more rapidly and more completely than we have modeled. These are not unreasonable suggestions. They are, in fact, the kinds of adjustments that cosmologists routinely make as new data arrives. Small recalibrations, refinements at the edges of the model, the kind of tuning that keeps a framework functional without requiring it to be rebuilt from the ground up. And it is possible that some combination of these adjustments will be enough. That the tension between the Webb observations and the standard model will be resolved not by revolution but by refinement. That future work will show us where we underestimated something, where a parameter was slightly off, where a physical process was less well understood than we thought. Science has resolved tensions this way before. Many times. It is in fact one of the most common outcomes when observations and models disagree. The model bends a little, absorbs the new information, and continues. But there is another possibility, one that the data does not yet confirm but also does not yet rule out. One that some cosmologists have begun to take seriously in the years since Webb began returning its extraordinary images. And that possibility is this: that the tension is not at the edges, that it is not a small adjustment waiting to be made, that the galaxies Webb is finding are not merely surprising but genuinely incompatible with the standard model in its current form, that what the telescope is showing us is not an anomaly to be absorbed but a signal to be followed, a thread, pulled gently, that may lead somewhere entirely new. To understand why some researchers believe this, it helps to understand something about how scientific confidence works. A single anomalous observation is rarely enough to challenge a well-established theory. Science requires reproducibility. It requires that results hold across different instruments, different methods, different teams working independently. A single galaxy that looks too massive and too early might be a measurement error, might be a misidentified object, might be a coincidence of projection or lensing that makes it appear more substantial than it truly is. A single data point carries very little weight against a framework built on decades of accumulated evidence. But Webb has not given us a single anomalous galaxy. It has given us many. Dozens of objects at extreme redshifts with properties that strain the predictions of the Standard Model. And as the mission has continued, as the observations have deepened and broadened and the spectroscopic confirmations have accumulated, the sample has grown. The pattern has persisted. And persistence is what transforms an anomaly into a problem. Persistence is what turns a whisper into a question that cannot be ignored. There is a concept in cosmology called the abundance of massive galaxies. It refers to how many galaxies of a given mass you expect to find in a given volume of space at a given point in cosmic time. The Standard Model makes precise predictions about this abundance. It tells you that as you look further and further back in time, into the earlier and earlier universe, massive galaxies should become increasingly rare. Because there hasn't been enough time to build them. The abundance should fall off steeply. The cosmic population of massive galaxies should thin out dramatically as you approach the first billion years. What Webb has found is that the abundance does not fall off the way the model predicts. At the highest redshifts, in the earliest epochs of cosmic time, there are more massive galaxies than there should be. Not a few more. Significantly more. The excess is not subtle. It is large enough that several independent research teams, analyzing different portions of the Webb data using different methodologies, have arrived at similar conclusions. The universe appears to have been building large structures earlier, faster, and more efficiently than the Standard Model allows. And here is where the conversation in cosmology begins to deepen. Because this is not an isolated problem. It does not stand alone. It connects, in ways that are still being explored and debated, to other tensions that have been accumulating in the Standard Model for years. Tensions that existed before Webb launched. Tensions that the new telescope did not create but may be amplifying. Making clearer. Harder to set aside. One of those tensions involves a number called the Hubble constant. It is one of the most fundamental numbers in cosmology. It describes the rate at which the universe is expanding. How fast space itself is stretching, carrying galaxies away from one another across the vast distances of the cosmos. Measuring it precisely has been one of the central projects of observational astronomy for nearly a century. Ever since Edwin Hubble himself first noticed, in the late 1920s, that distant galaxies were receding from us and that the speed of their recession was proportional to their distance. A discovery so profound that it reshaped our entire conception of the cosmos. That revealed to us, for the first time, that the universe was not static and eternal and unchanging but dynamic and evolving and expanding outward from a beginning in time. The Hubble constant carries his name. And for decades, measuring it more and more precisely was understood to be simply a matter of better instruments and better data. A refinement. Problem. The kind of problem science is very good at solving. Get better telescopes. Get better methods. Get better numbers. And eventually the uncertainty around the true value of the constant would narrow to something negligible. Something we could write down with confidence and move on from. That was the expectation. And for a long time, it seemed like a reasonable one. But something unexpected happened as the measurements improved. As the instruments grew more sensitive and the methods more sophisticated and the data more abundant, the uncertainty did narrow. The measurements did get more precise. But they did not converge. Instead, they diverged. Two independent families of measurement, using entirely different methods to arrive at the same number, began returning answers that did not agree with each other. Not by a small amount that might be explained by statistical fluctuation. By an amount that grew more statistically significant with each passing year of better data. An amount that now stands at a level of disagreement that cosmologists describe as a tension of roughly 5 sigma, which in the language of physics means that the probability of the discrepancy arising by chance is vanishingly small. So small that in particle physics, 5 sigma is the conventional threshold for declaring a discovery, for saying that something is real. In cosmology, this disagreement has been given a name. It is called the Hubble tension, and it has become, quietly and persistently, one of the most unsettling problems in modern physics. Here is the nature of the disagreement. One family of measurements derives the Hubble constant from the early universe, specifically from the cosmic microwave background, that ancient afterglow of the Big Bang that we mentioned before, that faint whisper of microwave radiation that fills all of space and carries within its subtle temperature variations an extraordinarily detailed record of the conditions that existed in the universe when it was only about 380,000 years old. The Planck satellite measured this background with exceptional precision. And from those measurements, using the standard model of cosmology to interpret what the data means, scientists derived a value for the Hubble constant. The universe, according to this method, is expanding at a rate of roughly 67 kilometers per second per megaparsec, which means that for every megaparsec of distance between 2 points in space, roughly 3.26 million light-years, the space between them is growing by 67 kilometers every second. The other family of measurements derives the Hubble constant from the late universe. From direct observations of objects in the relatively nearby cosmos whose distances can be measured through a chain of techniques that astronomers call the cosmic distance ladder. Cepheid variable stars, whose brightness pulses with a period that reveals their true luminosity, allowing their distance to be calculated. Type Ia supernovae, those brilliant and remarkably consistent stellar explosions that can be seen across billions of light-years and that serve as what astronomers call standard candles, objects of known intrinsic brightness whose apparent faintness tells you how far away they are. These methods, built and refined over decades, return a different answer. They suggest the universe is expanding at a rate of roughly 73 kilometers per second per megaparsec. Which does not sound like a large difference. But it is a difference of nearly 9%. And at the precision these measurements have now achieved, 9% is not a rounding error. It is a chasm. The two methods are looking at the same universe. They are measuring the same physical quantity. And they are getting answers that do not match. Either one of the methods has a systematic error that has not yet been identified, something subtle and hidden in the data or the assumptions that is skewing the result, or the standard model of cosmology is missing something. Something that affects the relationship between the early universe and the late universe in a way we do not yet understand. James Webb has touched this problem too. One of the early hopes for the telescope was that its extraordinary sensitivity and resolution would allow astronomers to measure Cepheid variable stars in galaxies further away than ever before, extending the cosmic distance ladder and either confirming or challenging the values obtained by earlier instruments. The results have been complex. Webb has confirmed some of the Hubble Space Telescope's Cepheid measurements with impressive precision, which suggests that the high value of the Hubble constant obtained from the distance ladder is not simply the result of measurement errors in the Cepheid data. Which means the tension does not go away. It remains. Stubbornly. Quietly. Like a stone in the foundation of a building that looks solid from the outside, but that those who designed it know is not quite right. And so we find ourselves, here in the dark, contemplating a framework that has explained so much and predicted so much and endured so much scrutiny, and yet that is now showing, at its edges and perhaps deeper than its edges, signs of strain. The early massive galaxies that should not exist. The Hubble tension that will not resolve. These are not the only anomalies. They are perhaps the most prominent ones, the ones that have received the most attention and generated the most discussion. But they exist within a broader context of questions and puzzles and small discrepancies that have been accumulating in cosmology for years. A collection of loose threads, each one perhaps individually explicable, but together forming a pattern that some researchers have begun to find suggestive. Suggestive of what, exactly, is the question that hangs in the air, that drifts through the data, that follows the light of those ancient and impossible galaxies as it travels across 13 billion years of expanding space to fall, finally, onto the cool golden mirrors of a telescope floating in the velvet silence of the Lagrange point, 1.5 million kilometers from the warmth of the Earth it left behind. That question does not demand an immediate answer. It does not rush. It has, after all, been waiting since the beginning of everything, since the first moments when the universe was small and hot and undifferentiated, before galaxies existed, before stars existed, before the long patient architecture of gravity had drawn matter into the shapes we recognize and name and wonder at. The question has been embedded in the structure of things all along. We are simply now, for the first time, sensitive enough to hear it. And what we are hearing, slowly, as the data accumulates and the images resolve and the spectrographs return their careful measurements of light stretched thin by distance and time, what we are hearing sounds something like this: that the universe may be stranger than our best description of it. That the map, however beautiful, however precise, however tested and refined across decades of extraordinary science, may not be the territory. That somewhere in the gap between the model and the reality, something is waiting to be understood. This is not a cause for alarm. It is, if you allow yourself to feel it fully, a cause for a kind of quiet wonder. Because every time in the history of science that a map has failed to match the territory, what followed was not darkness but illumination. Not the collapse of understanding but its expansion. Newton's gravity described the motion of the planets with breathtaking accuracy, and then, at the edges of its domain, at the perihelion of Mercury, at the bending of light around the Sun, it showed its limits, and those limits became the doorway through which Einstein walked, carrying with him a deeper and more beautiful description of space and time and mass and motion. The anomaly was not the end of the story. It was the beginning of a new chapter, stranger and richer than the one it followed. We do not know yet whether the anomalies we are seeing now, the galaxies that formed too soon, the expansion rate that will not agree with itself, are pointing toward a similar doorway. We do not know what lies beyond it if it exists. But there are those who are beginning to map its outlines, to trace the shape of what a new understanding might look like, and what they are finding is that the possibilities are numerous and strange, and in some cases almost vertiginous in their implications. One possibility is that dark energy, that placeholder name we gave to the thing we do not understand that is accelerating the expansion of the universe, is not a constant. That it has changed over time. That the universe is not expanding at the same rate it always has, not in the smooth and predictable way our standard model assumes, but in a way that has fluctuated, that has varied, that has a history we have not yet fully read. If dark energy is dynamic rather than static, if it has evolved as the universe has evolved, then many of the tensions in our current model might begin to ease. The early galaxies might find an explanation. The Hubble tension might loosen its grip. But accepting that possibility requires accepting something profound and unsettling, that the fate of the universe, which we thought we had calculated, which we thought we understood in its broad strokes, may be less certain than we believed. A dynamic dark energy is a dark energy that could change again, that could do things we have not predicted. The universe, under that interpretation, becomes less like a clock whose mechanism we have largely understood and more like a living thing whose behavior surprises us. Another possibility reaches further back, into the first fractions of the first second of existence, into the period we call inflation, that extraordinary and still not fully understood epoch when the universe expanded faster than light, when quantum fluctuations were stretched across the sky and became the seeds of everything that would ever exist. The details of inflation, the precise mechanism by which it began and the precise mechanism by which it ended, remain unknown. There are dozens of models of inflation, perhaps hundreds, and they make subtly different predictions about the structure of the universe we should see. If one of those models is correct, and it is not the one we have been assuming, then the initial conditions of our universe are slightly different from what we have calculated, and those differences, amplified across 13 billion years of expansion and structure formation, could manifest as precisely the kind of discrepancies we are now observing. The anomalies, under this interpretation, are not pointing toward new physics in the present. They are echoes of a different beginning. Faint signals from an inflationary epoch whose character we have not yet correctly understood, arriving now, across all of time, in the redshifted light of galaxies that formed when the universe was young. And then there are the more radical possibilities. The ones that live at the edge of what we currently consider respectable and peer, into territories that some physicists regard with caution and others regard with something approaching excitement. The possibility that dark matter, that other great placeholder, that name we gave to the invisible something that provides the gravitational scaffolding on which galaxies are built, is not what we think it is. Not a single particle, not a simple substance, but something with its own complexity, its own interactions, its own inner life that we have not suspected because we have only ever observed it through its gravitational shadow. We have inferred its presence from the way galaxies rotate, from the way light bends around clusters of matter too massive to be explained by the stars we can see, from the way the large-scale structure of the universe, that vast cosmic web of filaments and voids, could not have assembled itself from ordinary matter alone. We have mapped it, in a sense, without ever seeing it. We have weighed it without ever touching it. And yet we do not know what it is. This is one of the most remarkable facts in all of science. That the majority of the matter in the universe, not the majority of everything, that distinction belongs to dark energy, but the majority of the matter, the stuff that gravity works with, the stuff that built the galaxies and held them together and shaped the architecture of the cosmos, is something we cannot identify. We have been living inside a mystery of this magnitude for decades, and we have grown so accustomed to it that we sometimes forget how strange it is. How fundamentally incomplete our picture of reality remains, even now, even after all the satellites and telescopes and particle accelerators and decades of brilliant minds working at the edges of understanding. There are experiments running right now, deep underground in the quiet dark of old mines and tunnels, where the rock overhead shields the instruments from the constant rain of cosmic rays that would otherwise drown out any signal. Experiments that are waiting, patiently, for a single dark matter particle to interact with ordinary matter in a way that leaves a trace. A faint recoil. A small and fleeting pulse of light in a vat of chilled liquid xenon. These experiments have grown more sensitive with each generation. They can now detect interactions so rare and so faint that the mathematics of their sensitivity becomes almost poetic. They are listening for a whisper in a silence so deep it has no analogy in ordinary experience. And so far, the silence has continued. The most favored candidates, the particles theorists constructed with such elegance and such confidence, have not appeared. The whisper has not come. This too is data. Absence is information. The fact that the most natural and theoretically appealing dark matter candidates have not shown themselves in detector after detector, year after year, is telling us something. It is narrowing the space of what dark matter can be, pushing us toward either more exotic particles, particles stranger and lighter or heavier or more weakly interacting than the ones we first imagined, or toward something stranger still, toward the possibility that dark matter does not interact with ordinary matter in any way except through gravity, that it is gravitationally present but otherwise completely isolated, a ghost that leaves no fingerprint except the slow curving of space around its mass. Or toward the possibility, which some physicists have explored with great seriousness, that what we call dark matter is not matter at all, but a modification of gravity itself. That our equations of gravity, tested and confirmed across the scales we can access, break down at galactic scales, and that the missing mass is not missing at all but is instead a sign that we are using the wrong equations. These are not fringe ideas. They are serious scientific proposals, debated in journals and at conferences, tested against observation and found, each of them, to have both successes and difficulties. The universe has not yet told us which, if any, of these paths leads to understanding. It is withholding that answer with a patience that feels almost deliberate, almost sculptural, as though the revelation is being shaped slowly, the way something beautiful is always shaped slowly, with care and with time. And it is in this context of multiple unresolved mysteries, of dark matter that hides, of dark energy that may or may not be constant, of inflation whose details we do not know, of galaxies that formed too early and an expansion rate that disagrees with itself, it is in this context that the James Webb Space Telescope continues its work, continues its slow accumulation of data from the edge of time. Each observation adding another data point to a picture that is becoming simultaneously more detailed and more puzzling, more precise and more humbling. There is something almost meditative about the way science works at these scales. The timelines of inquiry stretch across careers, across generations. A question raised today may not be answered for 30 years. The data collected tonight may not be fully understood for a decade. There is a patience required, a willingness to sit with uncertainty, to hold a question without forcing it toward a premature resolution, that mirrors in some ways the patience required to simply be a conscious creature in an indifferent and magnificent universe. To look up, to wonder, to resist the temptation to fill the silence with something comfortable and instead to let the silence speak. And the silence, when you listen to it carefully, when you let yourself settle into it the way you might settle into deep and dreamless sleep, is not empty. It is full of information, full of signals arriving from unimaginable distances, encoded in the frequencies of light, carrying within them the history of matter and energy across 13 billion years of time. The universe is not withholding its secrets out of cruelty. It is simply waiting for us to ask the right questions, to build the right instruments, to develop the right frameworks, the right mathematics, the right conceptual vocabulary to receive what it has always been transmitting. We are, in this sense, students still, early in a curriculum whose full extent we cannot yet see, sitting in the first few rows of an auditorium whose back wall recedes beyond the reach of any light we have yet sent into the dark. And there is something in that image, the auditorium, the receding wall, the light that has not yet arrived, that captures something true about the situation we find ourselves in. We are not at the end of discovery. We are not even, perhaps, at the middle of it. We are at a moment of transition, which is both more uncomfortable and more alive than either the beginning or the end. A moment when the old framework is still standing but is visibly, undeniably showing its seams. When the new framework has not yet arrived, but its absence is beginning to be felt. When the questions outnumber the answers, and the most honest thing a scientist can say is not a conclusion but a direction. Not here is what we know, but here is where we are looking. The Webb telescope is looking, among other places, at something called reionization. This is one of the great transitions in cosmic history, a chapter in the universe's biography that we are only now beginning to read in any detail. In the beginning, after the Big Bang and after the release of that first ancient light we call the cosmic microwave background, the universe entered a period of darkness. Not the darkness of empty space as we know it now, scattered with the light of 100 billion galaxies, but a true and total darkness. A darkness in which no stars yet burned, in which the hydrogen that filled all of space was neutral, electrically balanced, not yet ionized by the ultraviolet radiation that stars would eventually produce in such abundance. This period is called, with a simplicity that contains within it something almost melancholy, the cosmic dark ages. And it lasted, by the best estimates we currently have, for somewhere between 1 and 200 million years. Then the first stars ignited. And this is where the story becomes, even by the standards of cosmology, extraordinary. The first stars were nothing like the stars we know. They formed from hydrogen and helium alone, without the heavier elements that populate the periodic table below and beyond them, the carbon and oxygen and silicon and iron that were forged later in stellar interiors and scattered by stellar deaths. Without those heavier elements, which astronomers call metals with a terminology that still startles newcomers to the field, the first stars could not shed heat the way modern stars do. They grew enormous, larger than any star that exists today. Hundreds of times the mass of our Sun, in some theoretical models perhaps 1,000 times. They burned hot and fast and violent, and when they died, which they did quickly by stellar standards, they released into the surrounding universe both new elements forged in their cores and intense radiation that began to strip the electrons from the neutral hydrogen that filled all of space. This process, the reionization of the universe's hydrogen, transformed the cosmos from an opaque and electrically neutral fog into the transparent and ionized medium through which light can travel freely, the universe as we observe it now. Webb is trying to see this transition, trying to catch the light from those first extraordinary stars, or at least from the first galaxies that collected them, in the act of reionizing the cosmos. And what it is finding, again, is that things happened earlier than expected. That the process of reionization may have begun sooner, may have proceeded faster than our models predicted. That the universe in its youth was more energetic and more structured and more complex than the calm and gradual picture we had imagined. This is a pattern. It is worth pausing to notice that it is a pattern, because patterns in science are not decorative. They are meaningful. They are pointing at something. Again and again, as Webb peers deeper into cosmic time, the universe it reveals is more organized, more mature, more fully formed at earlier epochs than our theoretical framework had led us to expect. The galaxies are too massive. The structures are too developed. The reionization may be too advanced. Each individual anomaly might have an explanation that leaves the overall framework intact. But the pattern of anomalies, the direction they all share, the way they all point toward the same conclusion, that the early universe was somehow more efficient, more rapid, more capable of complexity than we thought, this pattern is harder to dismiss as coincidence. It accumulates. It insists. And so the question that began with those early massive galaxies, the question of whether our cosmological model is complete, deepens with each new observation. It acquires new dimensions, new angles from which to approach it. Webb was designed to answer questions about the early universe, and it is doing that, faithfully and brilliantly, with an acuity of vision that still feels almost miraculous when you pause to consider what it is doing, measuring the redshift of light that left its source when the universe was a few 100 million years old, when everything we can see and touch and breathe was still hydrogen and helium drifting in the dark. It is answering questions. And in answering them, it is generating new ones, deeper ones, questions that reach beneath the questions we thought to ask, the way deep water lies beneath the surface of deep water, layer below layer, each one darker and quieter and more still than the one above. There is a concept in physics called emergence. The idea that complexity arises from simplicity, that from a small number of fundamental rules, followed faithfully by a large number of simple components, behaviors appear that could not have been predicted from the rules alone. That the whole is not merely the sum of its parts, but something genuinely new, something that did not exist at the level of the components and cannot be reduced back to them without losing what is essential. Water is wet, but no individual water molecule is wet. Consciousness arises from neurons, but no individual neuron is conscious. And perhaps the universe, in its large-scale structure, in its tendency to form galaxies and stars and complexity earlier and faster than our models predict, is exhibiting something like emergence at the grandest possible scale. A tendency toward structure that is built into the initial conditions or into the laws themselves in ways we have not yet fully understood. This is speculative. It is important to say that clearly, to hold the speculation gently and not mistake it for conclusion. But speculation, in science, is not disreputable. It is the necessary precursor to hypothesis, and hypothesis is the engine of inquiry. The great theories began as speculations, as someone allowing themselves to wonder what would happen if, what it would mean if, what the universe would look like if some assumption we had been making turned out to be wrong. Einstein wondered what it would be like to ride alongside a beam of light. That wondering became special relativity. The willingness to ask a question that sounds almost childish, almost too simple, and to follow it with absolute rigor wherever it leads. This is the method. This is how the map gets redrawn. And so there are those who are asking, with that same quality of patient and rigorous wondering, whether the initial conditions of the universe were different from what we have assumed. Whether the Big Bang, or whatever process generated the state of things from which our universe evolved, seeded the cosmos with more structure, more inhomogeneity, more of the gravitational seeds from which galaxies grow than our standard inflationary models predict. If the primordial power spectrum, the technical name for the distribution of those initial density fluctuations, the pattern of slightly denser and slightly less dense regions that gravity would eventually amplify into everything, if that spectrum had more power at small scales than our models assume, then galaxies could have assembled faster, could have grown more massive earlier, could have lit up the universe sooner than our equations told us to expect. The anomalies would not be anomalies at all. They would be the correct and faithful reflection of a beginning we had not correctly understood. Measuring the primordial power spectrum is one of the great challenges of modern cosmology. We have measured it across certain scales with extraordinary precision, using the cosmic microwave background, using the large-scale distribution of galaxies, using the subtle distortions that matter imprints on the paths of photons as they travel across the universe. But at the smallest scales, the scales that correspond to the first small galaxies and the first stars, our measurements become uncertain. The signal is harder to extract. The foregrounds, the intervening matter and radiation that can mimic or obscure the signal we are looking for, become more complicated. And it is precisely at these small scales that Webb is now beginning to provide new information, new constraints, new data points that will, over time, allow cosmologists to either confirm that the primordial power spectrum is what we thought it was, or to discover that it deviates from our predictions in the direction that would explain what we are seeing. This is slow work. It does not resolve in a single observation or a single paper. It accumulates, the way sediment accumulates at the bottom of a slow river, layer by almost imperceptible layer, until one day the geologist looks at the rock face and reads in it a history of unimaginable depth. The cosmologist's rock face is the sky, and the Webb telescope is reading it with a resolution and a sensitivity that no instrument before it could achieve. Each spectrum, each redshift measurement, each determination of a galaxy's stellar mass and star formation rate adds another thin layer to the sediment of understanding. The picture builds slowly, and then, sometimes, it shifts. The history of cosmology is punctuated by these shifts. Moments when the accumulation of data reaches a threshold and the picture reorganizes itself around a new understanding. When Hubble demonstrated that the spiral nebulae were not clouds within our galaxy but galaxies in their own right, each one an island universe of hundreds of billions of stars, The scale of the cosmos expanded overnight from something almost comprehensible to something that resisted comprehension entirely. When Penzias and Wilson detected the cosmic microwave background, almost by accident, in the hiss of a radio antenna they were trying to clean of pigeon droppings, the Big Bang moved from theoretical possibility to established fact. When the supernova surveys of the late 1990s revealed that the expansion of the universe was not slowing, as gravity would demand, but accelerating, the entire framework of cosmology had to be rebuilt around an unknown quantity, that dark energy, that placeholder, that confession of ignorance dressed in the language of mathematics. And now, here, in the data streaming back from a mirror made of gold and beryllium suspended a million miles from the warmth of the Earth, another threshold may be approaching. Another reorganization. Another expansion of the picture into dimensions the previous picture had no room to hold. The galaxies that should not exist according to the old framework are called, in the dry nomenclature of catalogs, massive early universe galaxies. But that phrase does not carry what they actually are. What they actually are is a problem wrapped in light that is 13 billion years old. They are structures of hundreds of billions of solar masses, galaxies as large and as organized as the Milky Way, appearing in the sky at a time when, according to everything we thought we understood about the way matter assembles itself in the dark, there should have been nothing like them. There should have been protoclouds. Diffuse halos of hydrogen, slowly condensing under gravity's patient instruction. The first stars should still have been young, burning with a violence that comes from their purity, their untouched primordial hydrogen, enormous and brief and solitary, not yet gathered into the swirling congregations that would eventually, over billions of years, become galaxies like our own. Instead, the Webb telescope found cities where there should have been wilderness. The process by which galaxies form is called, in the literature, hierarchical assembly. Small things come first. Density fluctuations in the very early universe, quantum whispers amplified by inflation into regions of slightly higher and slightly lower concentration, collapse under their own gravity into the first stars and the first small clumps of matter. These clumps merge. Over time, across billions of years, they accumulate into progressively larger structures. Dwarf galaxies become spiral arms. Spiral arms orbit around growing central masses. The whole edifice rises slowly, the way a cathedral might rise if its stones had no masons, no plan, only the patient arithmetic of attraction pulling toward across immeasurable distances and immeasurable time. That is the model. That is what the simulations predicted. That is what the mathematics supported and what the observations, for a long time, seemed to confirm. And then Webb looked back to within 500 million years of the beginning, and found galaxies that appeared to have already completed a process that should have required billions of years more than the universe had yet existed. They were not forming. They were formed. They were not assembling. They had, somehow, already assembled. Some of them showed signs of having already aged, of stellar populations that were old in a universe that was still, by any cosmological measure, very young. Red and quiet, the color of embers rather than flames, suggesting populations of stars that had already burned through their youth and settled into a slower, cooler phase. Stars grow redder as they age. A galaxy full of old red stars is a galaxy whose period of vigorous star formation has already passed. And yet these galaxies existed at a moment when, on any timeline we possessed, that period of star formation should barely have begun. This is not a small discrepancy. It is not a rounding error. It is not the kind of anomaly that smooths itself away when you gather more data or refine your calibrations. The more Webb observes, the more of them appear. Different regions of the sky. Different coordinates. Different distances. All of them returning the same quiet and unsettling answer to the question the telescope is asking. The early universe was more structured, more organized, more mature than the model said it could be. There is a word that astronomers use carefully, because it carries weight they do not always want to carry. The word is tension. When observations and models disagree, you say there is tension in the data. You say it in the measured tones of someone who suspects the ground beneath them may not be entirely solid, but is not yet ready to announce that. The Hubble tension, which preceded Webb and which Webb has only deepened, referred to the disagreement between different methods of measuring how fast the universe is expanding. Different methods, carefully done, by separate teams, using independent data, producing results that do not agree with each other. The tension has not resolved. If anything, it has grown more pronounced as the measurements have grown more precise, which is the opposite of what you would expect if the problem were simply one of imprecision. Now there is this. The tension between what the standard model of cosmology predicts for the early universe and what Webb is actually showing us is not a small one. It is not the kind of tension that a single elegant correction can dissolve. Some researchers have proposed modifications. Perhaps the efficiency with which early matter collapsed into stars was higher than the simulations assumed. Perhaps feedback mechanisms, the winds and radiation that stars blow back into the gas that surrounds them, suppressing further star formation, were weaker in the early universe and the process moved faster. Perhaps there are aspects of dark matter's behavior in the early cosmos that the models have not captured correctly. These are reasonable hypotheses. They are the kind of hypotheses that good science generates when the data pushes against the model. But they are also, each of them, an acknowledgement that something in the framework is incomplete. And there is another possibility, one that the more careful voices in the field raise only in measured tones, the way you might raise a question you are not certain you want answered. The possibility is not that the model needs a small correction, but that it needs something closer to what Hubble's discovery needed, or what the detection of the cosmic microwave background needed. Not a revision, but a reconception. Not a repair, but a rebuilding. The kind of shift that does not leave the previous framework intact with modifications, but replaces it with something larger, something that contains the old understanding the way a river contains the memory of the rain that fed it, present but transformed, no longer recognizable as what it was. This is an uncomfortable place for a science to find itself. Cosmology has spent decades consolidating around what is called the lambda CDM model. Lambda for the cosmological constant, Einstein's term, his so-called greatest blunder, reintroduced to account for dark energy. CDM for cold dark matter, the invisible scaffolding around which visible matter organizes itself. The model is not simple, but it is elegant in the way that frameworks become elegant when they survive long enough and explain enough and absorb enough confirming evidence that they begin to feel less like a theory and more like a description of reality itself. It predicted the distribution of galaxies across cosmic scales. It predicted the pattern of fluctuations in the cosmic microwave background with extraordinary precision. It gave cosmologists a language for discussing the universe that felt stable, that felt, if not complete, then at least sufficient for the questions they were asking. Webb is asking questions the model was not designed to answer comfortably. And yet the telescope does not know it is causing trouble. It has no awareness of the discomfort it produces in the offices and observatories where its data arrives and is analyzed and is compared against expectation. It simply does what it was built to do. It collects light. Ancient light, light that departed its source before the Earth existed, before the Sun ignited, before the Milky Way had taken its current shape, light that has been traveling since an era so remote that the universe itself was a different place, hotter and denser and smaller and structured in ways we are only beginning to see clearly. The telescope holds that light in its golden mirror and focuses it and records it with instruments of extraordinary sensitivity, and the data that results is simply what is there. It carries no agenda. It confirms no preferred outcome. It is, in the most literal sense, a message from the past, and like all messages from the distant past, it requires interpretation, And interpretation is where the difficulty lives. The difficulty lives there because interpretation requires a framework, and the framework is what is being questioned. When you look at a spectrum of light from a galaxy 13 billion light-years away, and you measure its redshift, and you calculate its distance, and you estimate from its brightness and its color the mass of the stars it contains and the age of those stars, every step of that process depends on assumptions. Assumptions about how stars form and how they age and how they radiate and how their light interacts with the gas and dust between them and us. Most of those assumptions are well tested. Most of them rest on physics that is solid and confirmed and reproducible in ways that leave little room for doubt. But most is not all. And in the space between most and all, in that small remainder, there is room for the unexpected. Some of the researchers studying these early massive galaxies are cautious. They hold the anomaly at arm's length and suggest that the resolution may lie in the details of stellar physics, in the behavior of dust at high redshift, in the complexity of modeling systems so far away and so ancient that every observation is filtered through 13 billion years of intervening space. This is the responsible posture. This is how science is supposed to move, slowly, skeptically, unwilling to revise the large structure of understanding until the pressure from the data becomes undeniable. The history of cosmology is full of anomalies that resolve themselves quietly, that turned out to be instrumental artifacts or modeling errors or the kind of statistical fluctuations that appear when you look at small samples of an inherently variable universe. But the sample is not staying small. That is the part that makes the cautious voices harder to maintain at full confidence. Every new observing cycle, every new pointing of the telescope at a new region of the primordial sky, returns more of them. More galaxies. More mass. More organization. More evidence that whatever was happening in those first few 100 million years, it was happening faster and more efficiently than the models allowed. The anomaly is not shrinking under the weight of additional data. It is, if anything, becoming more anomalous. And that is the behavior of something real rather than something coincidental. There is a particular kind of silence that settles over a field of inquiry when it begins to suspect that it is standing at the edge of something large. Not the silence of emptiness, but the silence of attention, of collective breath held, of instruments being rechecked and calibrations being reconsidered, not because anyone expects to find an error, but because the alternative, the possibility that no error will be found, carries implications that require a certain preparation before they can be fully absorbed. The community of cosmologists working with Webb data exists in something like that silence now. Papers are published. Conferences are held. The language remains measured, technical, appropriately hedged. But beneath the measured language, in the questions that get asked after the formal presentations, in the conversations that happen in hallways and over coffee in cities where the telescopes cannot reach, there is something that functions like anticipation. Not excitement, exactly, though excitement is present too, the particular excitement of a discipline that has spent decades mapping known territory and has suddenly glimpsed the edge of the map. Something closer to the feeling that comes before a long-awaited answer arrives. The knowledge that the answer is coming, that it cannot be prevented from coming, that the data will eventually accumulate to a point where the interpretation becomes unavoidable, and that whatever that interpretation turns out to be, the landscape of understanding will not look afterward the way it looks now. This is how it has always felt, in the moments before the large shifts. There is no announcement. There is no single paper that carries the weight of the change by itself. There is instead a gradual accumulation, a slow tilting of the balance between what the old framework can absorb and what it cannot, until one day the tilt becomes irreversible and the new picture resolves itself out of what had looked, for a time, like confusion. The confusion is not a failure. The confusion is the process. It is the texture of discovery at the scale where discovery actually changes things, where it does not merely add information to an existing map, but redraws the map itself around coordinates that did not exist before. Webb is generating that kind of confusion. And the universe, as it always does, is being patient about it. What the universe will not do is simplify itself to accommodate our understanding. This is perhaps the most important thing that the history of science teaches, and it is a lesson that has to be relearned in each generation because each generation arrives with a framework that feels, from the inside, like it might finally be sufficient. The ancient Greeks had a cosmos of nested spheres, perfect and geometrical and complete. The medieval astronomers had a cosmos centered on the Earth, with the heavens moving in circles around the fixed and special point of human habitation. Newton had a cosmos of absolute space and absolute time, a clockwork of such precision and clarity that it seemed to leave no room for surprise. Each of these frameworks was not simply wrong. Each of them was a genuine achievement of human understanding, a real approximation of something true, accurate enough within its domain of application to generate useful predictions and to organize experience in coherent ways. And each of them turned out to be a chapter rather than a conclusion. Lambda CDM may be a chapter. It is almost certainly a chapter. Not because it is wrong in the crude sense of being simply mistaken, but because the universe is larger and stranger and more various than any framework generated by minds that evolved to navigate the scale of savanna and forest and coastline can be expected to capture completely on the first attempt, or the second, or perhaps on any finite attempt. We are creatures of a particular size and a particular duration and a particular set of sensory capabilities, and we are trying to understand something that operates across scales from the quantum to the cosmic, across time spans from the Planck time to the age of the universe, across forces and fields and phenomena that bear no intuitive relationship to anything our nervous systems were designed to perceive. That we have gotten as far as we have is itself something close to miraculous. That there is more to go should not surprise anyone. And yet it still does. It still produces that particular quality of vertigo, that sensation of the floor shifting, when the data comes back from 13 billion years ago and says quietly, without drama, without apology, that something was happening out there that the model did not predict and cannot yet explain. The vertigo is appropriate. It is the correct response to genuine uncertainty at the frontier of knowledge. It is what keeps the inquiry honest. There is a phrase that appears sometimes in the papers, in the careful hedged language of scientific literature, that carries more weight than its technical surface suggests. The phrase is in tension with current models. It is a phrase designed to be precise and limited, to say only what the data strictly supports without overclaiming or sensationalizing. But what it means, underneath that precision, is that the universe has said something unexpected. That the message encoded in ancient light does not match the message that the theory predicted. That the gap between prediction and observation is wide enough and consistent enough and reproducible enough that it cannot be dismissed as noise or artifact or the kind of statistical shadow that disappears when the sample grows. The phrase in tension with current models is the scientific equivalent of a door opening onto a room that was not on the map. It is an invitation and a disruption at the same time. Webb has issued that invitation repeatedly now, in observation after observation, in dataset after dataset, in the spectra of galaxies so distant that the light arriving at its mirror left those galaxies before our solar system existed. Each set of data adds another line to what is becoming, slowly and unmistakably, a coherent picture of an early universe that was doing things faster, building things larger, organizing matter more efficiently than anyone had reason to expect. And the picture is not complete. It is far from complete. The telescope has been operating for only a small fraction of its intended lifespan, and already it has shown us enough to know that what remains to be shown will not make the picture simpler. The universe does not trend toward simplicity as it is examined more closely. It trends toward depth. Every answer opens into a corridor of further questions, and the corridor is always longer than it appeared from the entrance, and there are always more doors along its walls than the map suggested there would be. Consider what it means, in the most unhurried and careful sense, to see light that is 13 billion years old. Not to calculate it, not to model it, not to infer it from the behavior of other things, but to actually receive it, to have it arrive at a physical instrument and leave a measurable trace that human minds can then interpret. The photons that Webb collects from the most distant of these anomalous galaxies began their journey when the universe was a fraction of its current age, when the structures we live among, the Milky Way, the local group, the vast filaments and sheets and voids of the cosmic web, had not yet taken anything like their present form. Those photons traveled through the expanding universe for longer than the Earth has existed, longer than the sun has burned, longer than any geological record can reach, and they arrived at a mirror of gold suspended in the cold dark beyond the moon, and they were focused and recorded, and they became data, and the data became, in the hands of the people who study it, a question that the universe is posing to itself through the medium of minds that grew, eventually, from the same matter that those ancient galaxies were made of. This is not a poetic embellishment. It is a literal description of what is happening. The atoms in the human brain that processes the Webb data are composed of elements forged in stars, and some of those stars were already burning in the early universe, in the very era that Webb is now observing. The universe is, in some sense, examining its own past. The light that departed those ancient structures has arrived at detectors built from matter that those structures helped to seed, and the minds interpreting that light are the products of a long chain of physical and chemical and biological process that traces back, ultimately, to the same primordial conditions. There is something in this that resists ordinary language. Something that sits at the boundary between the scientific and the philosophical, that belongs equally to both without being fully contained by either. And it is in this context, in this strange loop of matter examining its own origins, that the anomaly Webb has found takes on a quality beyond the merely scientific. It is not just that the models are under pressure. It is not just that the timeline of galaxy formation needs revision or that the parameters of cosmological simulations need adjustment. It is that we are looking at the earliest structures of the universe and finding that we do not fully understand how they came to be, which means we do not fully understand how we came to be, which means the story we tell ourselves about our origins, the long story that begins with a singularity and proceeds through inflation and nucleosynthesis and recombination and the first stars and the first galaxies and the slow chemical enrichment of the cosmos that eventually made planets and oceans and life. That story has chapters we have not yet read. The chapters are there. They are written in the light. They have been traveling toward us for longer than any human concept of time can comfortably hold, and now the instrument exists that can receive them and record them, and the work of reading them is underway, and it is slow, because good reading is always slow, and because the text is difficult, and because every sentence opens into commentary, and the commentary opens into further questions, and the questions lead back to the text with new eyes that see things the first reading missed. Webb will continue to observe. Its orbit is stable. Its mirrors are performing beyond specification. Its instruments are cold and sensitive and precise in ways that took decades of engineering ingenuity to achieve. The mission is designed to last for 20 years, and if the telescope continues to function as it has, those 20 years will return an amount of data about the early universe that is difficult to fully imagine from the present vantage. Each year of observation will push the frontier further. Each new pointing will return light from sources that have never been directly observed before, from eras and distances that were, until recently, simply beyond reach. The picture that emerges from those observations may confirm the anomaly and deepen it. It may provide the additional data that allows the anomaly to be resolved within the existing framework. It may do something else entirely, something that is, by definition, not yet anticipatable, because anticipation requires a framework, and the framework may be precisely what is in the process of changing. What is already known is enough to alter the quality of the silence in which we contemplate the sky. The early universe was not what we thought it was. The process of becoming that produced everything, the stars and the galaxies and the planets and the slow chemistry of life and the minds that eventually looked upward and began to ask questions, that process operated in ways that our best models have not yet captured. And Webb is showing us this not as a failure but as an opening, not as the collapse of understanding but as its expansion into territory that was always there, always waiting, always holding its secrets in the patient way that the universe holds everything, without urgency, without concealment, simply present, simply real, awaiting only the arrival of an instrument sensitive enough and a mind patient enough to receive what was being offered all along. The offering is not simple. It was never going to be simple. The universe did not arrange itself for our convenience, did not scale its mysteries to the size of our attention spans or the duration of our scientific programs or the arc of any individual human life. It arranged itself according to principles that we are still in the process of discovering, principles that operate across scales and time spans so vast that our entire history of inquiry, from the first human who looked up and wondered to the engineers who folded a golden mirror into a rocket and sent it beyond the orbit of the moon, occupies a span of time so brief in the cosmic ledger that it would not register as a rounding error in the age of the galaxy's Webb is now observing. And yet here we are, asking, looking, receiving the light and trying to understand what it means. There is a kind of courage in this that does not get named as courage because it does not feel like courage from the inside. It feels like curiosity. It feels like the ordinary human desire to know, to understand, to close the distance between what is and what is comprehended. But to direct that desire toward questions of this scale, questions whose answers may not arrive within a single lifetime or a single century, to build instruments and train minds and develop mathematics for the purpose of understanding something so much larger and older than anything that built or trained or developed anything, is not an ordinary act. It is one of the stranger things that matter has done with itself in the 13 billion years since the universe began, and the strangeness of it, seen from a sufficient distance, is worth sitting with for a moment in the dark. The dark, for its part, is full. It is not the emptiness it appears to be from the surface of a planet, looking up through an atmosphere at the sparse scatter of nearby stars. The dark between the galaxies is threaded with the cosmic web, with filaments of dark matter and the galaxies that cluster along them like dew on an invisible spider's silk. The dark between the stars within those galaxies is filled with gas and dust and the magnetic fields that shape the birth of new stars. The dark between the planets in any given solar system is not empty but occupied by radiation and particle winds and the gravitational conversations between bodies that are always in the process of negotiating their paths. And beneath all of it, permeating all of it, the quantum vacuum, which is not empty either but seething with the virtual transactions of field theory, the constant quiet conversation of existence with itself at the smallest scales. Into this fullness Webb looks. Into this layered and ancient and structured darkness it sends its sensitivity, and what comes back is light, always light, the messenger that the universe has been sending across all of its distances since the first moments when matter and energy separated enough to allow photons to travel freely. Light from the early galaxies that should not have been so large. Light from stars that were old when the universe was young. Light that carries, encoded in its wavelengths and its intensities and the patterns of absorption that mark the elements it has passed through, the history of everything that happened between there and here, between then and now. We are at the beginning of reading that history. Not at the middle. Not near the end. At the beginning, in the earliest pages of a text whose full length we cannot yet estimate, learning the alphabet of a language that keeps revealing new letters. The anomalies Webb has found are not the end of the story. They are a deepening of it, a signal that the story is longer and stranger and more various than the previous chapter suggested. This is good news, even when it arrives in the form of confusion. Especially when it arrives in the form of confusion. The universe has more to tell us than we knew how to ask for, and the telling has begun, and the light is arriving, and somewhere in the data, in the spectra and the photometry and the redshifts of galaxies that existed before our star was born, there are answers to questions we have not yet learned how to formulate. And so the telescope holds its position in the cold and the dark, a million miles from the warmth of the only world we have ever known, its golden mirror open to the ancient light, patient in the way that only instruments can be patient, without hope or anticipation, without the weight of what the answer might mean, simply receiving, simply recording, simply doing the one thing it was made to do, which is to look and to look and to look into the deep and breathing dark, into the distances that hold the memory of everything, into the oldest light there is, which is still traveling, which has always been traveling, which will arrive in its own time, as all things do, carrying what it carries, saying what it says, to whatever is listening.